So in the last video, we saw that to solve a Conco-Homlindi, all you have to do is write down the auxiliary polynomial, factor it, and boom, you're done. Your solutions are going to look like e to the x, maybe x to a power times e to the x, and then that's it. There's sort of an asterisk in that, as this example shows. So if we have y triple prime minus y double prime plus y prime minus y equals 0, that's order 3. The auxiliary polynomial can be factored up to a certain point, right? But then you get this irreducible quadratic factor, d squared plus 1. You can't factor that completely over the real numbers. But the thing is, you can factor it over the complex numbers. Okay, so because this is a Conco-Homlindi, we've got 3 roots, so we should be able to come up with 3 solutions. They're going to be these 3 solutions. So e to the x, that comes from the root 1, and then you've got the root I and the root minus I. Each of them gives you e to the ix and e to the minus ix, respectively. Great. Well, except, like, what does that mean, man? E to the ix, what is that? So we're going to use what's called Euler's formula, which, if you haven't seen it before, is really just a definition of what we mean by e to the ix. All right, so e to the ix is cosine x plus I sine x, and if you put a minus sign, you get cosine x minus I sine x. Great, well that's fantastic. So now we can actually write our solutions down. Fantastic, except we still sort of have a problem. I mean, if this equation came about from modeling, say, the bouncing of a spring, and we're thinking of y as a position over time, well, we expect that to be a real number. We don't expect to have that be a complex number. So the question is, how do we get some real number solutions out of these 2 complex number solutions that we just discovered? And I've written them one on top of the other, so you can see if you add them together, those imaginary parts are going to cancel out. I went ahead and divided by 2 also, so that instead of getting 2 cosine x, I just get cosine x. We can do the same thing to isolate the imaginary part. You can see there that we're going to get a sine x. We have to divide by 2i because each imaginary part has an I in it. All right, why are we allowed to do that? Well, if y1 and y2 are solutions, this is a linear equation, then any linear combination of them should also be a solution, so w1 has to be a solution. And then the same for w2, right? w1 and w2 are just linear combinations of y1 and y2. So now we've got 3 solutions. And those solutions are real valued solutions, which is the kind of thing we're in the market for. All right, so this is one example, but the general principle holds no matter which polynomial you have, you can factor any polynomial, right, into linear terms and then some irreducible quadratic factors. Those irreducible quadratic factors are going to have some complex roots. So how do we handle the complex roots? Let's write down the general statement. The first thing to remember is that those complex roots occur in conjugate pairs. So if a plus ib is a root of a real polynomial, then a minus ib is also a root. The multiplicities with which r and r bar occur have to be the same. So if we call that same number m, there's going to be m solutions corresponding to r, m solutions corresponding to r bar, total of 2m solutions. And what we're going to do is pair them up and get cancellations of the imaginary parts, and then we're going to subtract them to get cancellations of the real parts. And at the end of the day, what you get is this. So you see that we still get this sine and cosine playing off each other. And then again, we get x, x squared, etc., all the way up to x to the m minus 1. If you count those, there's 2m of them. Great. Let's apply that in an example. Okay, so this is an order 5 equation. Let's go ahead and write down the auxiliary polynomial. And it turns out that that factors pretty cleanly. All right, that's factored all the way that we can. So the first root we're going to see is r equals minus 1. Let's take care of that right away. The other roots are given by solving r squared plus 4 squared equals 0. So r is going to be either 2i or minus 2i. So our solutions, looking at this result I've labeled the upshot, are as follows. We get e to the minus x, and then for each of these complex roots, we're going to get a sine and a cosine. We should realize that that's the same as 0 plus 2i, and that's 0 minus 2i. So a, in this case, is 0. So we'll just get cosine 2x and sine 2x, and then the algebraic multiplicity of this thing, we have a 2 here, a power 2. So we have to go up to 2 minus 1 is 1. And there we go, you can count them. We've got 5 linearly independent solutions. We're looking for a basis with 5 elements. We're done.